About exam 2, you now feel comfortable with the whole things now? Positive, negative, and then 4 factorial, you take some portion out based on some confounding factor, and if you don't have enough money for the fractions, you can do it block by block. But if you do it block by block, you don't want to use the sum of square in the numerator. You want to use in the denominator. Is that clear now? What I'm saying is that can you think it through yourself rather than plug and play? Okay? So let me just pretend, okay, this is not going to happen. Suppose that I have an exam 2A. I say exam 2A, the problem will be I have some x1. It's 3 factorial design. X2, example 2, variable 2 is 2 factorial, and variable 3, say, is 2 factorial. Let's do 2, just for now. Okay, so I have a sum 2 level and sum 3 level. Can you still come up with a 4 factorial design? Totally, how many treatments here? Totally, how many treatments here?
7.
Huh?
No.
How many treatments here?
Yes.
Huh? How many treatments here? Huh?
Not 7?
Of course not. Think about it. X1 could be, well, it's 3 level, right? So it will be -1, 0, and +1, right? But 2 will be -1 and +1. 3 will be -1 and +1. So if I want to come up with treatment for x1, 1, 2, 3, okay? What? Okay, so I can have this for 1, 2, 3. So here, just think about it. Can I have a -1, -1, -1? Can I? Yeah, so I can have a -1, -1, -1. What's going on? Yeah. So I can have -1, -1, -1. Can I have a +1, +1, +1? Can I have a -1, 0, +1? So totally how many treatments can I have? How many treatments can I have? Combinations. Come on.
I'm sure.
Well,
I was signing my autograph.
okay, here. If I have this, okay, x and x3. Let me start from x3. x3 I can have -1, +1, right? Agree?
Yeah.
So I can have this. Okay, and x2 I can have -1, -1, +1, +1. So just x2 and x3, our original 2 by 2. I have 4 treatment, right? Agree? So x1, since it's 3 level, first time I'll say that, hey, all of you is going to do -1, -1, -1. And this is one block, one combinations. And then can I have another combination? This time x1 is all at a medium level. And then one times all at high level. So totally, how many different treatment if I want to treat them as 1 by 1?
12.
12, right? So it's multiplications. And then if this multiplications, let's just say that I have to do it in 3 blocks. Okay? Would you block them this way? First time, beige block. Second time, gray block. Third time, green block. Would you use this 3 block to block the experiment?
No.
I don't want your answer. Kevin, can I block them in this 3 different level?
No,
Why?
because the next one is again the confounding.
Good job. Yeah. So I need to randomize this in order to make sure that they are not in line with this. So similarly, okay? If I said I'm going to treat them as 2 blocks, okay? Can I block them? I said, hey, I need to run this experiment in 2 blocks. Can I block it this way? Anything wrong with blocking this way?
I would say no.
Well, intuitively, okay? Anytime you see they block a line with some arrangement of in the data, most likely there's something gonna get confounded. So remember my dirty tricks, directly just using random number, and then like this, right? If I use a set of random number, okay, and then I'll say Control C, and paste value. Okay, and then I just call this run. Okay. And if I do it this way, sort by run. Okay? And then if I block them this way and block them this way, or block them somewhere in the middle, okay? At least you avoid using the high interaction term. So one thing you can do is what? Figure out, right? What will you have? First, low, 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 and then low, 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 low will be -1, +1. So figure out what will be the high level interaction term. The high level interaction term will be x1 times x2 times x3. And use that to separate the blocks. And when you do that, then you know that at least the main effect or the two-way interaction probably can shy away from it. You follow me now? So everybody show hands. You know there should be 12. I'm not running this kind because we're running out of time. We have other stuff more important to do. Everybody see there are 12 treatments, right? Second thing is that everybody see that directly just, 1 block, 2 blocks, 3 blocks, you're gonna run into trouble. So use some random number to separate them, to shy away from the main effect using high level interaction to do the blocks. This is kind of like an extension of exam 2, but the thinking, the logics, is exactly the same. You see that? Okay. So today we're gonna get into the response surface, okay? When we do the response surface, originally I didn't give you this, but I'm gonna do it now. Is I'm gonna use the Montgomery because some people say, oh, you didn't give us the textbook. That's why we don't know what to review. I'll give you some, but be honest with you, you read it, and then at the end, guess what you're going to find? Reading it, a lot of time, is a lot more painful, try to figure out the algebraic representation than playing with it. Okay? Okay, so all the exam problem gonna be one response was two variable. Okay? So I'm gonna stay with 2 by 2 for a while. Why? Because easy, just like using a 2 by 2 by 2, easy to visualize. The high level terms actually just doing the same thing, but everything makes sense. You know, randomizations or the stuff still makes sense. It's not like when you run into whatever you learn from the 2 by 2 by 2, it's going to be useful in any possibility. Okay, first, you can treat response surface as a regression. And since we're talking about a regression, keep that in mind for this class, okay? And this approach can solve, at least when I work in an industry, 99.9% of the problems, okay? So in other words, is that even though this is a simple approach, this is good enough, okay? And I also feel like if you don't fully visualize this, then the high level is wasting time. Okay, so for 2 level variable, so I have x1, x2, and then x3. How many different configuration or contour you think we're going to encounter? I kind of like talked about it last time. The world gonna be look like what?
Is it the baseball cap?
Ah, good job. So, but baseball cap, remember this, okay? Convex and concave really is the same side of the same coins. So in other words, is that if I have a response surface, say is concave, convex is holding water, okay? Concave, all you need to do is just use a very, very large number minus that things. Because once you minus that, the things will flip upside down, right? So that will look like a, so to me is max and min are the same coins, right? And second, okay, besides the convex and concave, what is the most tricky points we talk about? What is the most tricky point? We said that when we try to evaluate and find a good solutions, you know, concave and convex usually means, you know, max or min, okay? But there's a point that could be max and min at the same time. What is that point called?
Saddle point.
And saddle point depends on your perspective, right? You're looking from one direction or the other directions, okay? And they also quadratic form. So in other words, they all follow, you know, x1, x2. If I only using x1, x2, linear. If I have x1, x2, so first I can have x1, x2. Then I can have x1, x2 square. And then I can have x1, x2 interaction term. So put that down. If you don't have quadratic term, only x1, x2 linear, okay? That is called the steepest ascent or descent point. So in other words, is that it's work along the line. You'll find the highest points or lowest point. Agree? Right? Well, if I'm talking about this, how many of you ever seen rice paddy field in a mountain area in Asia? They're just layer by layer, right? And so if you want the water to run, smoothly, you just almost like walking on a step function from one layer to another layer. So we're doing this layer by layer. So you just vertically go by layer. You'll go up or come down. You agree with me? Think about it, okay? If I have a rice paddy field and I'm not walking vertical against that going up or going down, I'm going sideways. That means what? I'm going to be at the same level, agree? You guys follow me? The only way I can go up and go down is cross, vertical. Agree? Yeah. Okay. So I don't need to Google the picture. So regression, basically doing this, okay? The regression beta 1, beta 2, beta 3. The beta 1, beta 2, the regression beta really is what? Saying, here, if I have a beta 1, okay, equal to negative 3, y equal to beta 1 times x1, and beta 1 is 3. That means every time I increase x1 by 1, x1 from 1 to 2 to 3, y will increase by what? 3, 6, 9, right? So beta, if it's positive, will increase the y perpendicularly. Beta is negative, will reduce the y negatively. Everybody see that? Okay? Next, okay? We can have the quadratic form, okay? And when you have quadratic form, x1 squared or x2 squared, most likely, if beta for x1 squared or x2 squared is positive, that means what? That means when you increase x, y will increase dramatically. Okay? So, but on the other hand, think about it this way, okay? If keep adding x, no matter positive x or negative x, I'm talking about this term, okay? x1, no matter increase, x1 is positive or x1 is negative. x1 squared will be positive, right? So when x1 squared is positive, no matter x1 is positive or negative, just go up. That means that when beta is positive, this is convex or concave.
Be convex.
Okay, yeah, hey, interact with me, okay? If you don't interact with me and only interact with TA during the exam, say this problem is not covered in the exam, that's because you don't think with me. If you think with me, I cover everything in the exam, in the lecture 1, okay? Think with me. x1 positive or negative, beta increase, y will increase. As such, beta 1, if beta is positive, that means this is convex or concave. People, convex or concave. Here, x can be positive 1 or negative 1. No matter the positive 1 or negative 1, it's going up. So beta is what? Beta is positive, means it's convex or concave? It's convex, right? Holding water. Because if beta 1 is not holding water, how can you go this wall going up, goes that wall going up? Right? Think, okay? The exam problem, I promise you, I give you the Excel, I'm not going to let you plug and play. I want you to think about it. And the other thing is that I'm going to make the problem, I'll try my best. You cannot copy paste somebody else's answer. Okay? So if you don't think with me, and then, TA, do another sign-up sheet. So if people want to complain later, I'll say, you're not here. What do you complain about? Yeah, do another sign-up sheet. Yeah. Huh? Already did? Okay, good job. Yeah. Okay, think it through, okay? The answer is not that difficult. But the devil is in the detail. Okay, but then x1 times x2, that is the funky part. Remember what I said before in our experimental design, the single part. Interactions, no matter positive or negative, when we say there are interaction, what does that plot mean? When we say that, oh, there interaction, then the treatment plot won't be parallel, right? If they are not parallel, means x1 times x2, their value. And x1 times 2 got value, x1 and x2 got value. What does it mean? Is x1 positive, x2 negative is negative. x2 positive, x1 negative is still negative. But when x1 and x2 both positive, or x1 and x2 both negative, it becomes positive. So in other words, is what? Now it's diagonal. If I'm positive, negative on those two corners, then when they go up, things go up. But on the other hand, if I have one positive, one negative, one positive, one negative, what will happen is they'll go down. You follow me? This interaction term, y interaction term will become a tricky point. A saddle point, because we said x1, x2, they are not parallel. If x1, x2 are not parallel, means what? x1 times x2 could be both positive, both negative, or one positive, one negative. So in other words, diagonally, one go up, the other one come down, and this will be the saddle point. Okay? So far, so good. Okay, so three different configurations. Okay, the descent parallel, just go up, come down. Usually, that's the first things we're looking for. The second thing we're looking for is called stationary point. Stationary point, either top of the mountain or bottom of the valley. The third one is the saddle point. Okay? Whatever the landscape you're going to encounter, okay, you're going to investigate them locally. Locally means that there will be a local optimum, a local maximum, local minimum, or local saddle point. Okay? So far, so good? Next, okay? It's in your example. Always, for response surface, there are two different ways to look at the world. One is the regression way. So eta is the natural variable. Eta is 30, 150. So y equal to beta 1 times eta 1, beta 2 times eta 2, beta 3 times eta 1 square, beta 4 times eta 2 square, and beta 5 eta 1 times eta 2. You guys follow me? So I can treat y as how the world changed, and then everything changed. But the difference is in the exam, I probably will give you the landscape and say, hey, investigate the landscape. But in real world situations, I don't care where you work for. If you can see the response surface, you can have the entire landscape. You don't even need to investigate, right? You can just say, hey, that's the optimum. Go. You want max, I'll give you max. You want mean, I'll give you mean. But that's not the case. In the real world case, you only will start from four corners and then a center point. So this is one iterations of experiment. And then you, from that iteration, move to another iteration, to another iteration. Everybody agree with me? Okay? So now let's look at the things I would like to let you plot, okay? First, okay, if I have a variable, okay, And data set, I will give you, not gonna look so beautiful. Will be ugly. Okay? So I will have two variables, eta 1 and eta 2. And then I have the experimental variable, -1, -2, and this. So usually you will say that, okay, well, let me do it the other way first. Where is it? Here we go. So say I give you the response surface variable first, or the regression variable first, okay, and 75, whatever. And then I'll say that the design variable or step size, you basically will have this. Okay? You said the center around 85. Everything minus 85 divided by 5. And if you said that, why should I use 85? Later, I'll ask you, so what number you want to use? Could be 92, could be any number. And the step size, here I'm just using -5. And you said, oh, I don't want to use -5. The problem, I'm going to use the step size is, I'm going to use 7 or 7.9 per steps. Okay? And that actually will make a major difference among your answers. Okay? And it's not likely that if I give you a different starting point, you're going to end up using the same step size and center to calculate. But here, every variable will be, kind of like a z-score, minus mean divided by the standard deviation or scale to come up with either eta or x. Here is the same thing, either eta or x. Okay, so your step 1 is to decide, hey, where I'm going to start. So you will turn whatever the spreadsheet problem I give you. This is your step 1. Find your four corner and find your center and find the value. And this example here, pay attention, I did not add the epsilon, so it's not oscillating. But when you have your problem, I will give you the random noise like before. And the thing is that the level of random noise I'll give you this time will be good enough to make everybody's answer a little bit different. You cannot just copy-paste from other people's investigation. Okay? So far so good? Next. Okay? Every variable like here, I'm doing it the most complex way, is showing you that I have an intercept term, I have a linear x1, linear x2, x1 square, x2 square, x1, x2 interaction. Oh, no wonder I got a big mistake here. I think I made a mistake. Let's double check. Last one is, okay, let me double check one more time. Intercept 49, x1 50, 51, 52, 53, 54. So 54 is the interaction term. I made a mistake here. So let me redo it. Okay, so now you should follow my rule. Because I made it up every time. I don't follow. Okay, here's the sequence I use. You don't have to follow me, but this is the sequence I use. First, intercept. Okay? And then the second term, I'll use a linear x1, linear x2, quadratic x1, quadratic x2, and then the interaction x1 times x2. Everybody agree? So let me try this one first. Control C, paste. Okay, so see here, when you plug in a number, you will get a concave surface. Agree? And if you want, okay, sometimes I'll play with this. 3D rotation. No, I'll do this first. Change the scale. Where is the...
Did you do format axis at the bottom?
Oh, yeah. It's not bifocal friendly. I'll say probably, let's use 70. Oh, too much. 69. 67. Yeah, that's good. Okay. And then if you do 3D rotation, you'll see how the response surface change shape. Okay? But here, convex and concave, I'm going to show this once, because all you need to do is just minus everything by a very, very large number. We'll flip it upside down. Okay? Next, I'm going to do this one. This, I believe, is the settle point. Nope. This is this climb. Okay? Then let's try this one. This one should give you the settle point. Huh? Oh, I know why. That doesn't look right. Yeah. Let me double check. I think, the last two terms, I flip it. But since this is an example, all you care about is what? Would you guys agree with me that you can use x1 and x2 or eta 1 and eta 2 to create a response surface? Everybody agree? And the response surface, intercept plus x1, yada yada, the whole things. This is not a problem, right? You can do a 3D plot like this. Next, you can do the 3D plot rather than using the variable like this. You can use the variable of your eta variable. And later on, I'll show you, in SAS, just one click, you will get it done, okay? But here, everybody agree that we can plot the surface using two different approaches. Either we're using the true natural variable, eta 1, eta 2, or using the coded variable, -1, +1, -2, +2. To plot the surface. And the surface, if you change the parameter, let me do it one more time. Okay? If you change the parameter and said that, hey, give me different kind of parameter, and I'll show you how to use eigenvalue and eigenvector. Okay, this one is linear. So you know that going one direction is up, going the other direction is down. Or this one is linear. Okay? So What will be the one you would try at home? I don't care. It's just any quadratic form, okay? With how many parameters? With how many parameters to generate a form?
You said 2, right?
Well, no, the variable, we have x1 and x2. How many parameters can you have for x1 and x2? How many?
So you have the linear x1, linear x2.
Young man, count it. How many? I'll give you a hint. You have a term intercept. And what else? Do you have to have 2 linear terms? Right? So now I give you 3 terms. Young man, what else? What are the other terms you could have for response surface investigation? 2 quadratic terms and 1 interaction terms, right? So no matter what, if you look at the Excel, always just changing those 6 numbers. You change those 6 numbers, you move. So in other words, is that I'm doing a square dance, okay? x1, x2. And how big is the step size depends on how we define it. But once we define it is, I go x1, x2. Last time I already showed you. I increase or decrease, the variable go up or come down, right? So next example is exactly from the books. Example x11. So now, again, we just plot it, okay? If you plot it, yeah. So let's just plot it. This is the same thing. Oh, here we go. So let's consider this, okay? Here are the variable. And, don't treat it like the books. We just treat it like the example here. It said that I would like to start from this 4 corner. Corner 1 is 30 and 40. So let me, oh, this is nutty, that example. Okay, the example I give here is I start from the corner. Let me get rid of everything. Home. Okay, so you will start from, you identify where is your 0, 0. So you said my 0, 0 is at 85, and here's my center at 85. And I start from my 0, 0, where's my 0, 0? It's here, 175 and 0. Okay? You identify the center point. Step 1, you need to find your center point. And once you find your center point, you need to highlight your center point. And because once you highlight your center point, you can use the center point. Since I add a random number in there, you can repeatedly sample 5 data points. Or 3 data points. Agree? Okay. TA, take the notes here. So if they're gonna throw you a question in later and say, oh, Dr. Shang did not explain this, just throw them a note back. Okay? Step 1, you should have a coded variable and natural variable for x1, eta 1, x2, eta 2. Agree? So the world is either look at it naturally or look at it in a... So we need to identify the variable conversions between the two. So far, so good? Okay. Step 2, once you convert them into the two different worlds, okay? Usually, not usually, for this exam, you will say that, okay, where's my center? And then I'll identify my center and sample 5 times or 3 times. Depends on, how quick you want to get the answer. If you have a lot of money, you can sample 7 times. So far, so good? And once you highlight the center point, and then of course you need to know where is your 4 corner. So for corner 1, is start at 80 and 90. For x1, it's start at 80 and 90. Okay? In corner 2, and x2, you will find the other 4 points. So now you will say that I will have the negative 1 here and positive 1 here. Okay, so now if you have the center, can you identify the 4 corner points from the... If this is a real world situation, you basically run an experiment in order to get data points, 4 corner and several center points. Agree? And once you do that, you have your first database for your experiment collected. And we're not collecting the data through real experiment. We just say that I'll give you a plot to look at it. Okay? So everybody should be able to create this 5 column and 9 rows of table. Agree? And this 5 row and points, okay, is usually our starting point. And when we have this starting point, what are we really looking for? I'm looking from my center and said that which way do I go in order to, if I'm looking for max to get bigger, I'm looking for mean to get smaller. So I could just go or left or right, or I can go for corner. And of course, later on I'll say that, you know what, we probably go with a diagonal 22 degree. And how to calculate that 22 degree? Through eigenvalue, eigenvector. To find, in operation research, they say find a gradient. Okay? So, collect this data in order to do 2 things. Find the direction to move. Agree? Okay, before I go any further, can you think it through this way? You have a data set, and you need to figure out where is the center, what's your step size, so you can convert your variable, x1 and x2, into 2 different formats. One is the experimental design format, the other one is your whatever you're doing. the natural variable format. Identify the format, identify the center point, identify the four corner, you sample 9 points. You sample the 9 points, next steps, we can run a real experiment and do Excel, but now we're just using SAS. Okay?
So on the exam,
Mm-hmm.
what point would we be starting at? Like, what is given to us?
I probably will suggest randomly, well, actually, here's the things. Remember I showed you all the response surfaces are more than one local optimum, local minimum. So the things will be, here's the starting point, or identify 5 starting points to investigate the surface and see how many local optimum or optimum and minimum can you encounter. And now I'm not going to tell you how to do it, because if you do it right, you can investigate and find as many points as you want, if you understand how the experimental design works. But if you don't, you could sample, if there's a valley, okay, very, very flat and nothing there, you could get, remember last week I said you could get trapped in a local optimum? And the intelligence of this whole thing is when you work for the industry, you don't want to tell your boss. Your boss says that any discovery, any finding, I'm still looking for it. And what it really means is that I waste another batch of sample and get nowhere. So that is the, in other words, everybody can take experimental design. Everybody can do some sample. Everybody can dump it into SAS. But at the end, some people, 20, 30 data points, they figure out how these things work. And some people sample 200 data points and still get nowhere. Okay? This is North Carolina. You guys ever seen the documentary about Wright brothers? There are 2 competitions, one in New York, one in France. And how did Wright brothers come up with the best design to keep the airplane in the air? They try different things, right? And everybody knows everybody is competing on the Navy's contract, competing on who will get a big money, right? Well, how did Wright brothers did it? They figured out how to warp the wing by turning the airframe. So when the airplane start warping, the pressure differences, the Bernoulli pressure differences will be different, so they can glide through the air, right? And so for me is, everybody can run an experiment, but everybody can just waste money and get nowhere. How to, this one you just need to try and show that you can get there, right? So you follow me? The plug and play is going to be everybody the same. You all have the tools, but here's the part that I need you to do, okay? Okay, let me go through their approach first, okay? So if you read manually, okay, they will first obtain, once you have the data point, okay? I'm trying to say is that SAS will do it just one click, but here is how manually we're really trying to do. First, you need to estimate the error. How you estimate the error? Using the average of the center and the four corner. Okay, so the center and the four corners, that will give you the variations. And the second thing is that you will try to find if you can get rid of the interaction term. Okay, and why we want to get rid of the interaction term? Because if we're really start getting into, if we have, here, let me put it this way. If you know that you're already at, how should I put it? Okay, if you already know that you're at the max or the mean or the saddle point, what will be your major concern? If I say, Eureka, you find the warping effect of how to build the wing. You should be happy, right? But what will be your number one concern?
That it's a local optimum.
Or is it just accident? You know, just one time Eureka, it never repeatable. So the thing is that once we really find the so-called optimum point, we need to do some stretching investigation. But before we do that, basically we trying to say that, hey, there is no interaction term. What I'm saying is that at the beginning, okay, we want to have the model, but we want to make sure, okay, here, at the beginning, you only want beta 1, beta 2, those gradient, the linear term, significant. All the terms, interaction term, pure quadratic term, you want them to be what? Insignificant. Because if you found everything's quadratic term significant, on one hand, could be what? You're lucky. You really just one shot, you're already reaching the optimum. Agree? But there is another possibility is you don't really, well, if you're lucky, it means that you don't need to do anything anymore because you're already at optimum. But if you're not, okay, then we need to basically run the 3 steps after you get a data point. Are you still taking notes?
Yes.
Okay, so it's just 3 things, okay? He said it. Find the estimate error. Make sure that the cross product or the interaction term is not significant. The quadratic terms are not significant. If the quadratic terms are not significant, you know, x1 squared, x2 squared, and x1 times x2 are not significant. Means what? We still have opportunity to get even bigger. Then we can move to the next data point. You follow me? If immediately your quadratic terms and your interaction terms are big, means that, hey, I'm probably need to do some local investigation. Okay? And I'll show you how to do local investigation. But for your exam, I prefer you don't have that. Excuse me. So, if you don't have that, what is the beauty of it is you start from 0, 0, right? And then your natural variable is 35, 155, and then you have a step size you decide, and I'll show you how to decide the step size. So you just move x1 from 0 to 1 to x2 to 0.42, and move to 2, x2 move to 0.84, or 35, move to 40, 40 to 45, 45, 50, 55. Can you guys see? Natural variable is every 5 units, one step. But in experimental design is 1 to 2, 2 to 3. And here is a little smaller. And I'll explain to you how does that happen. But no matter what, you're looking for x1, x2, a square dance, in order to make your y get bigger and bigger. See that? Okay? And since I give you the response surface, you can just, plug in the stats and then and say that, hey, do I get my value bigger? If I don't get back to these things. Okay? You can tell this corner is 72. This corner is 81, right? Can you see that? So if I want to move max, that means which direction I should move to. 4 o'clock location or 11 o'clock. See here? If I want to find my max, where is my max?
Towards the bottom right corner.
Yeah, here is my max, right? So if you start from here, and then you just keep moving the other way. Well, not to mention, if you say you're looking for max, but you start seeing your value follow whatever you're doing, getting smaller, you plug in the wrong directions, right? And that's why I also showed you last week is that a lot of time I just look at the data point and said that I'm at the center, full corner, which corner give me bigger value? If they give me bigger value, I should move. If I'm looking for max, I'll move that directions. Which direction give me smaller value? For mean, I'll go that directions, right? So the next things you do is you need to use this ANOVA table, table 11.2. Repeat that again, and again. That's the documentation you need to have. And that documentation basically says that, hey, I'm getting significant on my beta 1 or beta 2, and I'm not having any quadratic effect, I'm not having any interaction effect. Because you have interaction effect or quadratic effect, you should stop and investigate. Agree with me? Okay? Yeah. Next, you can plot the improvement, iteration 1, iteration 2, iteration 3. Keep going and going. You should get bigger and bigger and bigger. And sooner or later, you'll overpass the biggest value and stop dropping. And if that happens, that means that, congratulations, you just passed the maximum value. Agree? And then, once you have the maximum value, okay, you need to run the experiment. When you pass the optimum value, and that's the max value or mean value, that means your quadratic term or your interaction term, at least one will be significant. Agree? Agree? You with me? You run this, you find a value, and you know that, hey, I'm reaching some points. Okay? And once you're reaching that point, okay, now we need to run and say, yay, I'm reaching a stationary point. The stationary means could be max, could be mean, could be saddle points. Then we need to investigate the saddle point. To investigate the saddle point, okay, now you need to collect the data, not just 9 points. Will be 9 points plus 4 more stretching points. Okay? And how to find those stretching points, I'll show it to you. How much time do I have? 5 minutes?
15 minutes?
Oh, it's not too bad.
Yep, 15.
Okay. And once we reach that data point, okay, the response surface, we need to investigate these things in what we call the quadratic form or the second order form. In the second order form, you need to have beta 1, beta 2. In our case, you only have beta 1, beta 2. So you will have a beta 1, beta 2, and then you will have a quadratic term, the capital B matrix. The capital B matrix, you also only have 4 terms. Actually, you will have a beta 1, 1, a beta 2, 2, and a beta 1, 2 divided by 2. Okay? So, this is why I ask you to remember how many terms you have. Beta 0 is the intercept, right? So we don't care. Beta 1, beta 2 are those linear terms, the direction to go up and go down. Okay? So we will have intercept plus the linear part. So your regression got this first 2 part. You agree? A intercept plus 2 linear part in this both B phase, beta 1 and beta 2. So far, so good? And then we will have a quadratic term, x1, x2 squared. In there, okay, really we only have a 2 by 2. The main diagonal is beta 1, 1 and beta 2, 2 for beta 1 square and for x1 square, x2 square. And the interaction term we will have is beta 1, 2. Okay? And why we need to build this? Because the first derivative equal to 0 tells us you have a stationary point. So first derivative equal to 0 means that b plus, this things is a quadratic term, right? Here, x, take the derivative, is b, small letter b, and then this quadratic term is x times x, so it's really kind of like x squared, so you have a 2bx. This thing's equal to 0. Then we know that my stationary point algebraically equal to this guy. Okay? And I know you don't want to see this. You want to see a numerical example. The numerical example require me to show you how to find the eigenvalue and eigenvector. Okay? And if, okay, this is something you can memorize for now, but gradually you will see that. If both eigen, okay, both eigen is positive, means what? Goes this way is positive, goes that way is positive. No matter which way I go is positive. That means this quadratic system, I'm at a minimum. So if lambda 1, lambda 2, no matter which way I go is, I know how to visualize this. People think about it this way, okay? Originally I say square dance, right? x1 increased, x2 increased. So you can consider I have the floor mark, step 1, step 2, this way, sideways and forward, right? But in reality, the data set basically, see here, if the data points or everything's lined up with the x1 and x2, then my eigensystem and my measurement system gonna be exactly the same. They're parallel. Okay? But in reality, the data, sometimes the orientation is like this. First of all, let me ask you this. Okay? I have x1 and x2 on the floor. How many different coordinate systems I can mark on the floor? First of all, where can I have 0, 0? I can have my 0, 0 any points I want, right? Can I mark the floor any points and say, this is my 0, 0? Can I do that? The second thing is that when I mark the floor is 2-dimension, Agree? So if I have a two-dimension floor, how many different ways I can say which direction is my y1, x1, which direction is my x2? Infinite, right? I can have any possibility. But here, the system we're doing is that we're saying that, well, having a long axis and a short axis based on your data structure, your response surface. So based on this, no matter x1, lambda 1 or lambda 2, originally it's this way. Now it's no matter it goes this way, long direction, okay, or the short direction, no matter which way I go, okay, I see my lambda value is going up. Then you know that this thing is holding water. Can you guys see that? If no matter which way I go, okay, my lambda is going down, going down. No matter I go left, go in W1 direction, going down, going W1 direction the other way, negative, going down, going W2 direction, going down, going this direction, going down. No matter which direction I go, it's down, down, down. So what will be this point? It will be max. So you see, if lambda is going down, down, negative, negative, then your point is a maximum point. If you go every direction, it's up, up, lambda is positive, then that is a is a minimum point. However, if I have one go up, one go down, and since the exam is two-dimensional, I could, in the real world, could be many variables. Some up, some down. That means what? I'm at a saddle point. You guys follow me? You know, could be going this direction is down, going the other direction is up. Then it got to be a saddle point. Agree with me? So you can consider this, okay? To investigate the stationary point, we need to come up with a new coordinate system. The coordinate system center around your stationary point. And we need to investigate the eigenvalue and eigenvector. If both eigen go up, okay, positive, positive, you're at the bottom. Both eigen go down, then you're at the top of the hill. One up, one down, you're at a saddle point. Okay? And again, this is a tricky point. You need to think it through. If you don't think it through, later on, if I say that here is a tricky response surface, how did you know what kind of topology you're in? You're not going to answer it. Okay? So look at this plot and this three value. Eigen value and eigenvector is a new coordinate system around my stationary point. And what does that mean? Okay? Can you see that? If you don't, show hands. Otherwise, no complaint later. You see it? Or you don't care until later. Okay? No objection 1, no objection 2. You're on your own. Next. So now I'm showing several different kind of response surface here. Okay? And during the response surface, people, have you noticed? I have 4 corner, 5 center point, and some stretching points. Okay? The red are the stretching points. And usually the stretching point, we're using these equations. If this is positive 1, negative 1, okay, the cage is what? How big is the cage? The diameter of the cage is 2, right? 2 by 2 by 2, agree? And so if, okay, I have a -1, +1. Oh, doesn't matter. Okay, and then -1, +1, and -1, +1. Okay, so for any 2 points, okay, would you consider me building a cage insert where's the insert data? No, insert graph. Oh, here we go. Doesn't look good. Well, it doesn't matter. Maybe I just use insert char. Okay, here are my 4 corners, right? So I'm at the center and I have 4 corners. And I said, hey, I'm at the center of 0, 0, could be positive, could be max, could be mean, could be a saddle point. But this could be accident. I just accidentally collect the data and find this point. Okay? How would you argue with your boss and say, no, this is a real thing. This is not fake. Hmm?
By picking one of those points and moving.
Well, but what I'm saying is, no matter which directions, right now I'm saying, no, I hear you. I'm not actually like your answer. I'm just trying to kind of like, be the devil advocate. Insert shape. Where's shape? There we go. Okay, here's my 4 corners, right? And I already said that among this 4 corners, man, I'm the king of the hill. I'm the top or the mean right here. Okay? And then how can you destroy me and say that, hey, your ego is too big, this is fake? One thing we can do is what? You only as good in this classroom. You only as good in this class. The minute you're out of the street, compete with NC State and Clemson, they're going to tear you apart. Then you know we're faking it, right? So what will be the best thing to do? Is you set up the boundary and then you stretch out a little bit. It says that, hey, I'm not only good inside the box, I'm also good outside the box. Agree? So once I said I find a box and said I'm good, okay? You could be faking it. It's, it's the psychology. You say to yourself, I'm good. But once you're outside the box, you're no good. So what we should do is go out a little bit. And how far out? Based on this, whatever the step size you have, then we just say that do a square root of what we call L2 norm. And then we need to stretch out this much. Now, think about it this way, okay? What if, this is not in the exam, but in the real world situation, what if I have 1, 1, 1, 3 of them? 3 dimensions rather than 2 dimensions. You're doing the same things. you need to do a square root of this one square, this one square. Well, if I have the square root of 3, you will stretch out even further. You follow me? So it's always, look at this, what do you see? Pythagorean theorem again, right? So we use the box to define our domain. And then we use the Pythagorean theorem that says that, let me destroy you. If I cannot destroy you, I probably have more confidence I'm at a saddle point. Okay? See you Wednesday.